Okay, so we are in part 3 of this acid-base chemistry chapter. This is our last part of this chapter, and then we'll move into the next chapter and talk about buffers and all kinds of cool stuff with acid bases. So we're going to finish this chapter today. And our objectives today, we're going to understand Kb. So we talked a lot about Ka and acid dissociation in part 2. So today we're going to also apply these principles to Kb and base dissociation. We're going to calculate pHs from Kbs. And then the last part is probably going to be the hardest part because we're going to look at ions. So now I don't have an acid or a base in solution. I have ions in solution, and seeing if those ions will react with water and as a result change the pH of that solution. So we're going to look specifically at ions moving away from sort of an acid-base scenario, but looking at when you have these ions in solution, is that going to change the pH at all, even though I don't have an acid or a base necessarily present? So that is our objectives for today. And if we look at a base solution, remember our definition of a base was something that our Arrhenius definition was a substance that produces hydroxide ions in water. Our Bronsted-Lowry definition was a base is something that is able to accept a proton from an acid. And so weak bases are going to be analogous to weak acids in that they only partially dissociate. And because they only partially dissociate, we're forming an equilibrium scenario. Okay, so here you see that there are a few strong bases. Just like there were 6 strong acids, there are 6 common strong bases. These are some of the group 1A metals and hydroxide and some of the group 2A metals and hydroxides. Weak bases are going to be very different, and a lot of times weak bases don't have hydroxide in their chemical formula, but instead act by pulling a hydrogen off of water and forming hydroxide in that fashion. And so here you see ammonia, NH3, is a very weak base, in that it acts by pulling hydrogen from water to form ammonium polyatomic ion and then the hydroxide. This is methylamine. Methylamine is also a weak base. So a lot of these weak bases have this amine group, this NH2 group in common. And here you see are some KBs for some weak bases. And so this is the same table that is in your equation quick sheet that I had. And here you have, instead of a Ka, you have a Kb. And you see here we have methylamine. That's a NH2 group. That's what's pulling the hydrogen off of water. This ethylamine, same thing. Ammonia, same thing. Pyridine has a nitrogen in it that's going to pull that hydrogen off of water. And aniline, the same thing. So you have this amine group here. So oftentimes if you see some organic compound that has an NH2 group on the end, oftentimes that'll act like a weak base. Here is some structure. So this blue is the nitrogen. So this just shows that this nitrogen, because it has this lone electron pair here, it can act like a Lewis base donor and pull a hydrogen off of water. We could treat these just like we treated Kas. So if I have a base, and we'll just say generic base B, and I have that in water, if it's a weak base, it's going to partially dissociate and form BH+. So it's going to pull a hydrogen ion off of water and hydroxide ion. So it's going to partially ionize here. And this would be a weak base, which means it's going to have a Kb. So my Kb for this, my base dissociation is going to be my products, so BH plus OH minus over, and since water is in the liquid phase here, it doesn't need to go into the mass action, and it's just going to be over B there. If I have a strong base is going to completely dissociate. So a strong base is going to form BH plus OH minus. But most of our strong bases, if you recall, most of our strong bases already have a hydroxyl group. So most of the strong bases that we're going to run into, at least in this chapter, is going to be some metal hydroxide plus water is going to form the metal ion plus hydroxide ion and then still water. So since this is a strong base, it's only going to go in one direction, and I'm not going to have a Kb associated with that. So I would just take my initial starting concentration of this, and that's going to give me my concentration of hydroxide ion. I'm not going to do any problems with you on this, but calculating Kb, find pH. Let's say I have this weak base here, and I start with 0.01 molar of my base, and I want to know what is the pH of this solution. The first thing that I'm going to do is I'm going to set up an ice table, and I'm going to solve for hydroxide ion concentration. Once I get hydroxide ion concentration, then I'm going to use that and my K box, if you remember our K box here, and I'm going to find my either pH. I'm either going to go this way to find pH, EOH to pH, or I can go this way and find H3O plus and then get to pH that way. So there's two ways to do that. I can take my hydroxide ion concentration and then get to my pH that way. So this is going to be a lot like what we did with Ka, but instead of solving for hydronium ion concentration, when you use a Kb, you're always solving for hydroxide ion concentration. So these are the calculations that we're going to do in our Zoom meeting when we come together and do that both in part 2 and in part 3. We're going to look at Ka and Kb calculation. The last thing that we wanted to cover in this chapter was what happens if you have an ion. So sometimes ions and salts will act like acids or bases, and they'll change the pH of solution. And they're not going to look like acids or bases. So we're not going to be able to tell just by looking at them. We're going to take each individual ion and see how that is going to affect the solution. So we're going to consider each ion individually, and if it can react with water to either produce H3O plus or OH minus. So if it produces H3O plus, then it's creating an acidic environment. If it produces OH minus, it's producing a basic environment. So we're going to look at each ion, if I have an ion or if I have a salt. So remember, salt is a generic term for an ionic compound. So I either have the ions or I have the whole salt, and I've dropped it in water, and I want to know, is that going to change the pH? Will that change the pH at all? So there's no mystery here. It's just kind of thinking about what can happen when you have these ions in solution. So the first one we'll look at are anions. And remember, anions are negatively charged, and anions have the potential to act like a base in water. Not all of them, but some of them do. That means that they can react with water to produce hydroxide ion in solution. So if I have an anion and it has the potential to act like a base, it's going to make that solution basic, because what it's doing is it's producing hydroxide ions in solution. And so that'll make your whole solution basic. So let's look at some anions and talk through whether that's going to happen or not. So let's say I have an anion, I have chlorine ion, and I have fluorine ion. So I have these two ions in solution, and I want to know, are they going to change the pH of my solution if I add those ions in? Will they change the pH of solution? And if I add chlorine to water, in order for it to change the pH, if anions are going to react, they're going to always react as a base, which means they're going to pull hydrogen ion off of water. If chlorine were to react with water, I would form HCl and OH minus. But what do we know about HCl? This is a strong acid, so it's never going to form. It's always going to disassociate. So this isn't going to happen. So chlorine is going to have no effect. So my pH will still remain neutral. It'll be whatever it was before I added the chlorine in. So if I have the anion of a strong acid, it's not going to have any effect. But here I have the anion of weak acid. So in water, this can form an equilibrium mixture with HF and OH minus. And because this is a weak base, then that can happen. So this scenario here is plausible. And so that means that if I have fluorine ion in solution, it's going to act like a weak base in that it's going to accept a proton from water. It's going to form this weak acid and hydroxide, and this is going to drive the pH. Even though I'm forming a weak acid, this is where my pH is going to come from. This is going to drive the pH and make it basic. So if I have an anion and it's the anion of a weak acid, it's always going to have this effect where you're going to form this equilibrium scenario and you're going to produce some hydroxide ion, which is going to make the pH more basic, so raise the pH. If I have a cation is going to be different. So cations, like anions, cations are going to be positively charged, and they can have the potential to react with water and act like an acid to produce hydronium ions. So anions are going to act like a base, cations are going to act like an acid if they meet these criteria. So if it is the counter counter ion of a strong base. So if I have calcium 2+, or let's look at, so calcium 2+, or sodium plus, or K+, these are all counter ions of a strong base. CaOH2 is a strong base. NaOH is a strong base. KOH is a strong base. They're going to keep it neutral. So they're not going to react with water to form hydronium ion. Because what would have to happen is you would have to have calcium ion reacting with water, form CaOH2, which is going to leave a hydrogen ion, which is going to quickly react with another water, hydronium ion. In order for this to act like an acid and react with water to produce this, it's going to have to pull the hydroxyl group off of water. But since this is a strong base, this is not going to happen because this is not going to exist in solution because this is a strong base. It will not form in water, so you're not going to produce any of this. Your solution is going to remain neutral. So any of those counter ions that are counter ions of a strong base, so calcium, sodium, potassium, lithium, strontium, and barium are all going to remain neutral. They're not going to react with water. If I have a counter ion of a conjugate acid of a weak base. So I have a conjugate acid of a weak base. And let's use NH3. So NH3 is a weak base. It's going to react with water to form NH4 plus and OH minus. This is a conjugate acid of a weak base because this is my weak base. So this is my conjugate acid base pair. If I have a conjugate acid of a weak base and I add that to water, so let's say I don't have any of this, I just have this, and I add it to water, what's going to happen is it's going to donate hydrogen to water to form H3O plus and NH3. So it's going to go back to the weak base. This is an equilibrium scenario. So if I have the conjugate acid of a weak base, it can act like an acid in that it donates an electron to water. This is going to make the solution acidic. So it's going to change the pH of that solution by donating a hydrogen to water to form hydronium ion. So it's going to act like an acid and donate a proton. So if I have a conjugate acid of a weak base, it's helpful to recognize your weak bases. So NH4 plus is always going to be the conjugate acid of the weak base NH3. So if I have that as a counter ion, that's going to make it acidic. And then the last thing is if I have the small, highly charged metal ions. So we looked at this first, and that had no effect. My counter ions of a strong base. We looked at the conjugate acid of a weak base, and that's going to make it acidic. And the third thing I'm going to look at is the highly charged metal ion. That's going to act like an acid because it's going to form hydrates in solution. And I'm not going to really go into much about this except to just to note if you have this highly charged, and these are usually small metal ions, highly charged meaning +2, +3, +4, so that would be something where you would have a really strong charge. And when it forms in water, it's going to form this complex, this Lewis acid-base complex, and that's going to change the pH of the solution. I don't really talk about that very much in this chapter, and we'll come back to it in later chapters if we get there. But let's just go through a couple examples of this. On your sheet here is I kind of went through some of these classifications. So these are the ones we just went through, anion and cation. And then if I have a salt, I'm going to look at both components of the salt. NaFCa2H3O2 KNO2. I'm going to look at these individual salts and I'm going to see, will the addition of each of these salts change the pH of solution? So the first thing is I'm going to take them individually. So I'm going to look at NaF first, and I'm going to look at each individual ion. So in NaF, I have sodium ions and I have fluorine ions, and I'm going to consider them separately and figure out what effect are they going to have on that solution. So sodium ion, this is the counter ion of a strong base, so it's going to be neutral, no effect. Fluorine is the conjugate base of a weak acid, and my weak acid is HF. So if I'm not sure, I'll just add an H to this and see if that's one of my strong acids. If it isn't, then it's going to be a weak acid. Conjugate base of a weak acid, so that's going to act like a base in that it's going to pick up a proton from water and it's going to make it slightly basic. It's going to produce hydronium ion. So if I take sodium fluoride and I add it to water, my pH is not going to be neutral, it's going to be slightly basic, and that slightly basic is coming from the fluoride ion. If I look at calcium acetate, calcium ion is the counter ion of a strong base, and that's CaOH2, so that's going to be neutral, there's going to be no effect. C2H3O2 minus is the conjugate base of a weak acid, and that weak acid is acetic acid, HC2H3O2, so it's going to be slightly basic. So if I add calcium acetate into solution, it's going to increase the pH of that solution, it's going to be slightly basic. Now if I look at NO2, KNO2, K plus and NO2 minus, K plus is the counter ion of a strong base, KOH, so it's going to be neutral, no effect. NO2 is the conjugate base of a weak acid. My weak acid there is HNO2, so it's going to be slightly basic. So in this case, for all three of these, if I add these into water, and if I was taking the pH of that water, I would see the pH go up. So it would become basic. What if I take sodium hydrogen carbonate? Is that going to change the pH? And if so, how? So I'm going to break this into ions. So this is going to give me sodium ions and HCO3 minus ions. So I'm going to recognize this as the counter ion of a strong base, NaOH, so that's going to be neutral. This, however, is the conjugate base of a weak acid, and that weak acid is H2CO3, carbonic acid. So this is going to make it slightly basic. Let's do one more page of examples, because I think these are a little bit hard to think about. So aluminum bromide, and I dissolve that in water. First off, I'm going to look at my ions. So I'm going to have aluminum ions, and I'm going to have bromine ions. And so aluminum ions, this is a small, highly charged cation, which is going to act slightly like a weak acid. So it's going to make it slightly acidic. Aluminum is small, and having lost 3 electrons is going to make it highly charged. Bromine ion is the anion of a strong acid. So it's going to be neutral and have no effect. So if I add aluminum bromide to solution, that pH is going to go down, it's going to be slightly acidic overall. If I look at CH3, NH3, NO3. So I recognize this guy. This is the nitrate polyatomic ion. And then this whole thing here is going to be positively charged because NO3 is going to have a negative charge. So that means CH3 NH3 is going to have a positive charge. This is going to be one of those conjugate acids of a weak base. And that weak base is CH3 NH2, so methylamine. So if this is acting like a conjugate acid of a weak base, then that's going to make it slightly acidic. NO3 minus, this is the anion of a strong acid. My strong acid is HNO3. That's one of the 6. So it's going to be neutral and have no effect. So overall, if I add this to water, it's going to reduce the pH and be slightly acidic. Let's look at one more. NH4F, ammonium fluoride. So my ions here are NH4 plus and F minus. And so NH4 plus is the conjugate acid of a weak base. That weak base is NH3, so that's going to be slightly acidic. My F minus, this is the conjugate base of a weak acid, HF, so that's going to be slightly basic. I'm going to look at my K values here to see which one is going to be bigger. If I want to calculate it, I would do my Ka for NH4 plus and my Kb for F minus and see which one is greater. If Ka is greater than Kb, then that means it's going to be slightly acidic. If my Kb is greater than my Ka, then it's going to be slightly basic. So I could work that out. And you'll notice if this is the conjugate acid of a weak base, this means that I'm going to find a Kb for this, but I'm not going to find a Ka. If this is the conjugate base of a weak acid, I'm going to find the Ka for this, but I'm not going to find the Kb. To be able to use a Ka and a Kb for this, you need to calculate them. There's a handy little shortcut that allows you to do that relates these together, and that's Kw. That's the autoionization product constant for water is equal to Ka times Kb. So for instance, if I'm given Ka and I want to find Kb, then I can just take Kw and divide by Ka, or vice versa. So if I have a scenario here where both of them are contributing, I'm going to want to back up, compare K values, and then I can see which one is greater. That's going to drive the pH of my overall solution. And we might do one of these problems when we come together in our Zoom meeting. So this ends this chapter on acid-base chemistry, and so I hope to see you in our Zoom meetings, and then our next pre-recorded lecture we're going to start talking about buffers.